So where things left off last time was looking at sunlight in the various ways, the circumstances in which sunlight breaks up into its constituent colors, in effect, the rainbow colors. Just to remind you then again, so sunlight consists of this broad swath of the electromagnetic spectrum. It has, within sunlight, there are radio waves, microwaves, millimeter waves, infrared light, visible light across all the colors, all the rainbow colors, red, orange, yellow, orange, yellow, green, blue, violet, and then off into the ultraviolet. So that's all represented in the rainbow spectrum. On the full spectrum of sunlight, normally it arrives all together, and we see white light with our eyes. There are circumstances in which those colors get separated in various ways. The sky is blue because Rayleigh scattering preferentially redirects the short wavelength portion of the light that goes through it. The particles are better scatterers of the short wavelength stuff than they are of the long wavelength stuff. So the blue light gets scattered, the red light's left, and you see the setting sun. Rainbows, that separation was a different phenomenon. Actually, it was a bunch of phenomena altogether. To get a rainbow to work, you need reflection, refraction, and dispersion. Remember, reflection was this phenomena where waves, whenever they encounter a change in speed, if they speed up or slow down, they partially reflect. And refraction comes about because when light, or any wave actually, tries to go from a medium in which it travels at one speed into a medium in which it travels at different speed, it bends. If it doesn't hit the interface between those two straight on, it bends. It bends toward the perpendicular. If it slows down, it bends away from the perpendicular if it speeds up. And lastly, dispersion was this effect whereby the different wavelengths of light, or alternatively you can label them by frequency, they travel at different speeds in typical materials. So glass, various forms of glass and so on. The blue light typically travels more slowly than the red light. It gets behind if you're trying to send information. It also bends differently on entry and exit from glass, or from water. And so that's the origin of the rainbow. Are you okay with how a rainbow works? I'll leave that behind us. Questions about rainbows? The soap film was yet another way to separate the colors of light in sunlight. And it was using an effect generally known as interference, where waves can interfere with one another or with pieces of themselves. And the idea of a wave having different pieces, well, if you have a water wave, wave, and it encounters, picture a wave on the surface of water. If it encounters something, a pillar or the rocks, a big rock out there, the wave can get broken into pieces, and the pieces can ultimately travel different paths and arrive at the same place. And when they do, if the crests are together, you get a very big crest. If the crests are opposite one another, they're fighting each other, you get a very wimpy crest or nothing at all. So those are interference effects. And they show up in any wave phenomena. They show up. And they show up particularly nicely in light when light encounters thin films of something, like an oil slick on water. The rainy puddles, if they get oil on them, you'll see colors reflected off that oil film. The soap bubble, same thing. And the physics there was waves. A wave of sunlight, and there's a question coming up that I want to ask. I'll just tell you. Sunlight, again, it's like buckshot. It's lots of little waves, all independent of one another. Different wavelengths, heading in different directions. Just off it comes. Each of those waves originated with some charged particle on the sun's surface jiggling around. And the interference is within one of those waves. Each one of those waves has the opportunity to undergo interference. It goes into the soap film. Ignore all the other waves in this buckshot. You're looking at one little shot. It goes into the film. Part of that wave reflects right off the top surface. Part of it enters the film, bending in the process, bounces off the back surface, returns through the film, and then breaks free. It ultimately ends up going the same direction as the first portion of wave. So you've got two portions of the same original wave, the majority of which incidentally goes through the film and leaves. You're only getting about a total of about 8% of the wave coming back at you. And those two pieces that together are that 8% can interfere with one another. They're traveling the same direction. They started as the same wave, so they are well suited to interfere with one another because they have the same electric field up, electric field down, and so on. But one of them might be delayed relative to the other by virtue of having traveled farther. So one piece is behind the curve here, and if it traveled just the right distance farther so that it's moved on to the next electric field up compared to the first one, which was electric field up, the two electric fields are together, they overlap right. So that the two electric fields from the two pieces simultaneously point in the same directions, and they experience constructive interference. Questions about that idea of having a wave, crack it in half, overlap it, but shift one portion in space and time, such that this crest, these two are the same crest before the crack, but there was a second crest here separated by that distance, one wavelength, and it's lined up perfectly. So the two crests are working together to make a bright light. That's okay? That's called constructive interference. It's possible for a different wavelength of light traveling this same path, a light of a different wavelength, a little wavelet traveling with a different wavelength. It won't necessarily, here are the two original crests again lined up like this, but where's the next crest in this shorter wavelength light? Well, it's over here. It's behind, and what is present for this portion of wave to match up with the one in my right hand thumb? It's upside down. So you can get waves that traveling this path interfere with one another destructively. They're pointing the wrong way. The electric fields are opposite one another. Consequently, they cancel, and you see nothing. So the soap films, and there are lots of devices, items in modern life that use interference to break the colors up. The crazy color reflections you get off of discs, CDs, DVDs, Blu-ray, that's interference effects too, and there's jewelry that does this, and it used to be rare. It's now dime a dozen getting these things that play with waves, light waves, crack them into pieces, overlap them in funny ways, and get either constructive or destructive interference, and ultimately typically look very brightly colored. Okay? So that's the world of interference. One last thing to talk about with sunlight. So these are all breaking up the colors. One last thing to look at, and I'm just going to buzz along to this. When you buy sunglasses, so there's a little bit of a public service announcement aspect to this thing. When you buy sunglasses, you're often given the opportunity to choose polarizing sunglasses or not. I mean, the purpose of sunglasses, of course, is to look good. But apart from that, partly protect your eyes and partly to see things you wouldn't otherwise be able to see very well. Well, it turns out that glare, the light that reflects at shallow angles off of surfaces. So you're driving down the road, the sun is off in the distance overhead, and there's a lot of light that's skipping off the pavement, off your front hood, skipping up into your eyes, and you're dazzled by glare. Or equivalently, you're at the seashore or at a lake. The sun's over there in the distance in front of you, and it's skipping off the lake and dazzling you, right? This is all familiar. In that kind of circumstance, you can't look into the lake. You can't see anything inside the lake because all you're seeing is a reflection of this brilliant reflection of light coming up off the surface. That's, why is the light skipping up like that? It's the usual reflection. Even asphalt, you think of asphalt as really pretty black stuff. Road surface is very black, but it's it is not metallic. It is transparent, at least it's a non-conductor. And if the light hitting its surface isn't absorbed immediately on entry to the surface, because it's basically think of it as a dark plastic. Not quite right, but it's close. It's a plastic that's full of black ink. Well, even black plastic doesn't necessarily absorb all the light that hits it within one wavelength of the surface. The light has to actually go into the plastic a little bit before the little black things in there gobble it up. And that means that you can get a reflection off the surface anyway. You've all noticed that there's such thing as black paint that's glossy. It's got a nice bright reflection, but it's black. Where's the reflection coming from? It's coming from the fact that the light hitting the surface changes speed. It's going into plastic after all, and it's not air to plastic. That's a change in speed, and so some of it reflects. It basically reflects before it has a chance to have been absorbed. So you get, that's what a glossy black paint does that. It allows the light to go in more than one wavelength of light, give or take, and before being completely consumed, and therefore you get some reflection anyway. You get some reflection off of asphalt. You get a reflection off of almost anything non-metallic, and certainly everything metallic. All right. Well, when you're driving along or looking at the lake, you might want to not be looking at this glare all the time. Is there a solution to the glare? And the answer is yes. It turns out that the glare, so that, I'll turn on a light here and make some glare. What are my chances of not dipping my tie in the oil that's here? We'll see. So many of you may be able to see glare coming off this table. And if you can't, I will use the camera to stare at it. 1 second here. So the camera is now going to stare at that glare, right? This light that you're seeing here is being reflected by the top surface of the table, which has a thin plastic lacquer on it. Wood itself tends to just send light in all kinds of directions, so it's so rough that it doesn't make a good glare, but that flat plastic lacquer certainly does, beat up as it is. And that's what you're staring at as you're driving along. Can you get rid of it? Well, it turns out when light reflects straight off of a non-conducting surface, like right off of glass, you look at a window and you see your reflection straight back at you. The light that bounces off has no polarization. Doesn't matter. That is, if a little wave comes off your face, heading toward the window, and it happens to be polarized vertically, it hits the window, it will come back as a vertically polarized wave, and you'll see it. Similarly, if it was horizontally polarized, this is electric field. I should tell you what my thumb means. It doesn't mean thumb. It means electric field. Okay. Hits the wave, comes back. The reflections are equally good. In fact, the window doesn't care about polarization when you hit it straight on. There's no way it could sense polarization, really. But if it hits at a shallow angle like this, polarization suddenly matters. If the wave coming off that light was vertically polarized and it hits the surface, when it skips, it'll remain essentially vertically polarized. Vertical polarization becomes kind of an approximation when it's tilted away from true vertical. So there are physicists have names for these. This is called P polarization when it hits like that, as opposed to this is S polarization, but who cares? The names don't matter. The point is, this wave skipping deals with the surface differently from a wave rotated 90 degrees that hits like this. And I've got videos of this in the book, the electronic book. You can watch the videos of these two kind of reflections. The reflection where the wave is, and now I'll leave that for the moment and just talk here. A wave that has an electric field vertical like this, that hits the floor and bounces up, doesn't reflect very well. It has trouble moving the charge in the surface, sort of lifting the charge up and down, lifting it out of the surface, pushing it down. It doesn't polarize the surface the same way as a wave that is polarized horizontally. The wave that's polarized horizontally pushes charge back and forth across the surface. And the response of the surface is much more effective at reflecting for that charge pushed across the surface as opposed to charge that's pushed up and down in the surface as it tries to skip. Long and short of it is, the reflection that is glare, that you're, look, there, oh, duh, sorry, yeah, brain freeze. The reflection that is glare there, that's almost all horizontally polarized light. That camera doesn't notice. It's oblivious to polarization. Light is light as far as it's concerned. But there are materials. It's actually remarkable that they exist. This is a giant polarizing filter. It's the equivalent of, you can buy them for your glasses. They're smaller. It passes only one of the polarizations and it absorbs, it gobbles up the other. So I look dimmer right now, also kind of foolish here, framed, because half the light has been absorbed. And I don't know which one's horizontal, which one's, we'll find out in a minute. The point is, I'm claiming that that light is almost exclusively horizontally polarized light. The vertically polarized light failed to reflect, went into the plastic and wood, and was absorbed by the wood. So, to show you that that's true, I'll put here. This is now passing, the filter is passing horizontally polarized light. Basically no effect, right? If I rotate the filter 90 degrees so it absorbs, so it passes only vertically polarized light, the glare is just consumed almost completely. So it's a real effect. When you buy polarizing sunglasses, they are designed to absorb horizontally polarized light, the light that is most common in glare. If you want to see whether your glasses are polarizing or not, find a place that's full of glare and rotate your head 90 degrees. The glare will suddenly reappear and it'll go away when you return. Okay? I mean, other fun things to do with polarizing are 3D, when you get 3D glasses these days for movies, are they polarizing things? Like the old 3D glasses, I haven't been to a 3D movie yet, like not in memory. The old 3D movies were different colors, red and blue. Is that what they are now? No. They're colorless, and they're non-electronic, right? They're like cardboard thingies. Okay, so they must be polarizing. In which case, when you look at other people, you see one eye. The other person, only one eye. If you look through one eye, you see only one eye of other people. Is that true? Anyway, normal sunglasses block horizontal polarized light. Those ones for 3D movies, almost surely, one eye blocks horizontal, one eye blocks vertical. And if you look at somebody else, your eye that sees horizontal will see their eye that sees horizontal. But your eye that sees horizontal won't see their eye that sees vertical, because you'll have the two filters fighting each other. All right. So, if you're there in a room full of people with some sunglasses and your sunglasses are polarizing, meaning that they block horizontally polarized light, if you turn your head at 90 degrees, all the people in the room who have polarizing sunglasses, their eyes will disappear. You won't be able to see them because their glasses will be blocking all horizontally polarized light. Yours will now be blocking all vertically polarized light, and that gets rid of everything. All right? Fun and games. That's all I have to say about sunlight then. Any questions about sunlight, things you wonder about? Random stuff. Okay. I'll turn off the glare and go back to normal view over here. Okay. So the next topic is discharge lamps. And the method in my madness here is sunlight is a beautiful, so it's the ultimate example of thermal light, of light that is produced by virtue of something's temperature. Sunlight originates at the sun's surface because of the sun's high temperature, nearly 6,000 Kelvin. Not all light comes, however, from hot objects by virtue of their temperature. There are other ways of making light. And sort of as a background to this, up until somewhere last century, light was all the light anybody ever dealt with was thermal light. If it didn't come from the sun, It came from a candle or something like a candle of fire. Also, a thermal source. You're looking at light produced because of something being hot. Incandescent light bulbs. Again, light produced because of something being hot. Somewhere, with rare, any other exceptions. There are probably some exceptions, but basically all lighting was thermal. Sometime in the last century, people figured out how to make light without a hot object, to sort of synthesize light creatively. And the original sort of series of things that did this were what are called discharge lamps, which include neon sign lamps, the fluorescents that are illuminating this room still, the highway lights, that the mercury vapor lamps that, for example, that are used in big box stores and gymnasiums, that when the power fails, it takes about 5 minutes for them to turn back on. You know those lights? I mean, alas, for better or worse, a lot of these are they're all going to go away and be replaced by LED lights, which is the third topic here. So the discharge lamps is the middle topic in the world of light. The third topic that we'll get to is LEDs and lasers, which are even more sophisticated ways of synthesizing light. And as you head into these more sophisticated ways of synthesizing light, it becomes more energy efficient. Producing light with a hot object is energy inefficient because most of the first of all, you have very limited control over the colors and wavelengths, and a lot of the light just falls right outside the visible. So with an incandescent light bulb, only about 10%, or maybe not even that, about 10% of the power that you put in as electricity comes out as visible, usable light. The majority of the power you put in comes out in other sort of forms of heat, including infrared light. And that's not, it's okay if you want to, easy bake ovens, do they still have easy bake ovens around? Do they still operate with an incandescent light bulb in there as the heat source, or have they changed that? Yeah. So, incandescent light bulbs are great for easy bake ovens, but they're really not very good for lighting. All right. Okay, so, to start off here with a question, a fluorescent lamp, so these things overhead, or the compact ones that you can screw into an old-fashioned lights fixture, they have a white powder on the inside of the glass. So if you've ever broken one, you've discovered it actually really is full of powder there. And if you got rid of the powder, what would you see in the lamp? So if we got rid of the powder, there's white powder inside the glass tubes up there overhead. Imagine getting just, boof, the powder's gone. What would you see? And I give you three choices. It would be brighter, it would be dimmer, it would be about the same brightness, but there would be an unpleasantly bright white line in the middle of the tube. You okay with the question? Just for fun. How many think it would be brighter? How many think it would be dimmer? How many think it would have an unpleasant white light line right in the middle? Okay. Just for fun, because I get good at coming back to my questions, bad at coming back to my questions. This will be effectively a fluorescent lamp without the powder. That's dazzlingly bright. If the powder in there, that would be really bright. It's really dim, right? The problem is, this thing's emitting mostly ultraviolet light. And that's what those tubes would do. They'd be mostly glowing ultraviolet, and you wouldn't be able to see much. And so part of my story is to explain, so what's the powder doing? It's not just acting as a sort of a diffuser to get rid of a bright white light. It's really involved in creating the white light. That powder is necessary. It's not just any old powder. It's called a phosphor, and it's a very sophisticated powder that does a useful purpose. We'll come back to it. Okay, some observations about discharge lamps is typically they take a moment or so to turn on. They've gotten so sophisticated now that they turn on pretty fast, but there are still some that take a while. You've surely noticed that things like the highway lights, the ones that remain, that haven't been replaced, they take 5 minutes to warm up. You watch them kick on at sunset, but they start really dim and messy and funny colored, and then they work their way up to full brightness. You can get these discharge lamps in a whole variety of colors. All the signage lamps are all discharge lamps. They may also eventually get killed off by LEDs, but the true neon signs, for example, such as you've all seen that light and that color. That's real neon sign. And the light in that is coming really from the gas inside that tube. Incidentally, what discharge means is that tube is carrying an electric current. So it's a gas that is carrying electric current. That's a discharge. How do you get it to carry current? Well, you get some charges into the middle of it, and you put electric fields on it, and you shove them back and the charges back and forth. You get them to collide with each other and knock more charges out of other gas atoms, and eventually you get this electrically charged gas. It's a gas that has charges in it, can carry electricity because current can move long distances in it. It's technically known not so much as a gas anymore as a plasma, but that's not important. Anyway, that's, the signage is these gas discharge lamps. Fluorescent lamps are also discharge lamps. Highway signs also. They often hum loudly. This guy hums. It's driven me crazy for years. That's not so much the lamp as the power source for it. It has loose stuff in it, and it's a transformer with loose aspects to it. And as we all know, transformers involve magnetism, right? And alternating magnetism, so the power moves from primary to secondary. Well, if everything's not tight, that movement of power also involves physical movement. Stuff actually jumps around magnetically. And so this whole box vibrates. You can hear the hum, right? That's the famous 60-cycle hum. That's associated with our power grid. That's the frequency at which the alternating current's reversing. It's a sad part of life. That noise is everywhere. Okay, that's good enough. So the questions to go after, why phase out incandescent light bulbs, and then sort of the whole story of these, this new series of lights that involve gas discharges, the flow of electric current through gases. So, as I said earlier, thermal light sources they're all somewhat inefficient, because even the sun produces a fair amount of infrared and ultraviolet light, neither of which are any good for illumination. Here on Earth, we can't make things as hot as the sun that will last any period of time. So an incandescent light bulb runs as hot as it can without having its filament die so quickly you can't stand it. And the temperatures of a typical incandescent light bulb filament are only about half that of the sun. So it's dimmer, it's far redder, it's really short on blue light, and so it's not a very good simulation of sunlight. That line there about being less than 10% thermal power, I mean, even the best incandescent lamps only put out about 10% of the power in as visible light. They really squander it. All right, so you can do better if you stop using a hot surface to make light, rather synthesize it strategically so nearly all the power that you put into the lighting unit ends up as visible light. And probably the most extreme case of success in this matter are what are known as low-pressure sodium vapor discharge lamps. Sodium is an element, part of table salt, sodium chloride. Sodium, it turns out, now I'll show you, not today, but on Monday, sodium, when you make it, normally it's a metal. It's a very reactive metal. It's a lot of fun. If you throw it in water, it bursts into flames. But anyway, if you get the sodium metal hot, you can get sodium atoms to come off it as vapor. And if you run a discharge in the sodium vapor while it's kind of a thin vapor, it emits this intense yellow light. It is extremely energy efficient, but it's one color, this yellow, and that's it for all practical purposes. And so there was an era when sodium vapor, low-pressure sodium vapor lamps were really common on highways, and they were hideous to drive in because it's one color. The world was yellow and black, nothing else. And it actually messes up your depth perception. There's sort of no nuance to the light. And eventually they all went away. Even though it's more energy efficient than anything else, including the LEDs, it's just such a one-colored lighting that you couldn't stand it. Okay, so how can the colored lights mix so we can see white? So if you're going to try to create visible light and usable visible light, like not just yellow, you're going to want to make us see white. And as I said last time a little bit, the way we see white has to do with how our eyes evolved. We actually only have 3 types of color sensors, and the white light, when we see white, it's because those 3 types of color sensors are all responding and saying, I see light. And your brain synthesizes that observation as, oh, we're looking at white. And this time I brought out, this is an old demonstration I haven't used for years. So this is a box with three lamps inside. There's a blue lamp, there is a green lamp, and there is a red, green, blue. I can't talk and play at the same time. So there really are only 3 colors present in this box. There's red, right? Oh, I can't. I can't even do one thing at a time. There's green, and red, green, blue. You all hear that? And if you bring 2 of them up together, for example, green and blue, we see what's known as cyan. And if we bring green and red together, we see yellow. And if we bring red and blue together, we see magenta. And if we bring all 3 of them together, we see white. This is just how your brain works, interpreting those colors. I mean, it may not be the greatest white. You have to balance this properly. We have to turn off the room lights to do it. But basically, there is, right here, there are 3 specific colors present that a spectrum analyzer type device would say. They would say, there's some green here, there's some red here, there's some blue here. And our eyes look at that and go, we see that as white light, or something close to white. All right? People have studied our optical sensors. And again, this is like what's normal. For normal people, the usual vision people have, they have red sensors that are most sensitive right around 600 nanometer wavelengths. But light tapering off towards longer wavelength and towards shorter wavelength is still triggers these sensors. And there's this strange recurrence over here in the blue that your red sensors again begin to see the light a little bit out here in the blue end of the spectrum. You also have green sensors and you have blue sensors. And the reason you see yellow up here, so that yellow there, on this projector, there is no yellow light there. That is really, this is the projector's red lights. This is the projector's green light. At this location, if you come up here and look closely, you'll see that it actually consists of little red spots and green spots. There is no yellow. It's just your eyes, unable to resolve those red spots and green spots, see them both as overlapping. And both sensors go, wow, we see light, and your brain interprets that as yellow. Here also, there is no cyan here. It's just the presence of blue and green simultaneously makes you see cyan. And magenta over here is when you see red and blue. And those names, cyan, magenta, yellow, these are familiar to you as the pigments for a color printer. Color pigments are complementary to color lights. Color lights, the 3 primary colors are red, green, and blue, and that has to do with how our eyes work. It's not just somebody from Crayola saying, well, we're gonna pick those 3. Those really are the way our eyes work. And if you want to find the primary colors of pigment are the pigments that selectively absorb one of the 3 primary colors. Cyan pigment absorbs red. So if you put it on the paper, all the red goes away. Magenta picks out green. Yes, magenta picks out green. If you put magenta pigment on a paper, there's no green light reflected. And finally, yellow pigment, absorbs blue. So if you put it on paper, no blue light comes out. So if you put those three pigments on together, no light comes out, you see black. But you can work with those three. So the three primary colors of light are red, green, and blue. The three primary colors of pigment are yellow, magenta, and cyan. And it's not arbitrary choices. They're determined by how our eye color sensors work. Okay? Questions about color? You can start looking at color printing and color illumination. All your gadgets, look fine enough, you will see red, green, and blue spots. They're tricking your eyes into seeing any color. All right, so on into why does a neon lamp emit red light? And the story immediately gets complicated because it has to do with quantum physics, quantum mechanics, quantum whatever. People sometimes, just as an aside, people talk about quantum physics as though it were a discipline to study. It has rather become, it certainly was in the early 1900s. People would actually do their research on quantum physics. At this point, it's so well established and of such broad utility that it's a tool like a mechanic reaches into the toolbox and pulls out a wrench. So nobody studies wrenches anymore. Just like very few people study quantum mechanics itself. It's just a tool we use all the time. So why do I need quantum mechanics? Because the red light that you're seeing here is why is it red? And it's actually more complicated than just a single red. Quantum mechanics underlies that whole story. So I have to talk a bit about quantum mechanics. That's true of other parts of discharge lamps. There are a whole lot of quantum mechanics stuff. So a little bit about quantum mechanics. You may have grown up thinking of these subatomic particles like electrons and protons, neutrons, as little tiny balls, little tiny objects of well-defined shape and size. Well, they're not, it turns out. In fact, nothing really is quite as simple and solid as it appears to us. But that's particularly true as you get to look smaller and smaller. You discover that, well, things have not just a particulate nature that is like a billiard ball. It clearly looks like a ball. If you make the billiard ball smaller and smaller and smaller, it'll still look like a ball. Eventually, it'll start to have a noticeable character that's not ball-like. It will have a character that is wave-like. And that's true of electrons and atoms. So if you look at, or in matter in general, electrons in, let's just pick an atom just to talk about something specific. The electrons in atoms are not just little balls orbiting around the nucleus of the atom. So an electron does have a negative charge, and it is attracted to the positively charged nucleus of the atom, and it does therefore center its life and activities around the nucleus, being attracted thereto. But while it's in the atom, it's not a little planet orbiting the nucleus. Instead, it's a wave around the nucleus. And particularly, it's a type of wave known as a standing wave, a wave that doesn't go anywhere, that just sort of dances in place. It's just waving in place. And just to give you an idea of what I'm talking about by a standing wave, we'll play jump rope here for a second. This is a one-dimensional medium or a venue in which to show you a wave, and it's one-dimensional because it's only got a length. And I can make it dance like this. This is a standing wave on a spring. If you've ever played jump rope and not done it on an app, this is what it looks like, right? Approximately. Although you might go around in a circle, it's the same effect. So this is one standing wave that can live on a spring. But the spring, being a complicated structure with lots of pieces of spring, it can move more than one way, for example. So this is one. And if I go twice as fast, I should be able to try to keep it under control. This is another standing wave. It's got a crest and a trough simultaneously. Now, the structure isn't going anywhere, it's just dancing in place. There's a dead spot in the middle known as a node. You can see right in the middle, nothing's happening, or pretty much nothing. If I go 3 times as fast, can if I'm lucky, I'll get the third. Once it gets out of control, it's hopeless. I'm trying to. Anyway, you get the idea. Really, go take care of yourself. Anyway, these are standing waves on a spring. They're not moving along the spring, they're dancing in place. And it turns out an electron in an atom, it lives not in orbits where it's going around and around. It lives as standing waves around the nucleus. And you might think, well, but what's waving, and where's it waving to? Well, an electron, unlike the string, is a one-dimensional object that can wave up and down into a second dimension. In this case, the dimension that the wave lived along was left to right, and it was waving into up and down as sort of the dimension it was of the wave. For an electron in an atom, it's a three-dimensional wave, and it waves into, well, it can't go to another dimension, we're out of them. It's got a three-dimensional structure as a wave, and the waving goes into some other, come on, there. These are the standing waves, the simplest standing waves of an electron in a simple atom, like the simplest atom would be a hydrogen. So there's a positively charged nucleus here at the center of that hydrogen atom. So that's actually just a proton. And living around the proton is a standing wave. It's a spherical standing wave that is the electron. And what is it waving to? Well, in my drawing here, it's waving from red to green. Red, read the colors right. Red to yellow to green to blue to red to yellow to green to blue. It's waving through the colors. It's cycling through the colors. That's the wave cycle. But the structure of the wave is just a sphere. And the electron is simultaneously in that entire sphere. It's a little more complicated than that, but it lives around the proton in this wave structure. There are other waves that are possible. For example, here's a two-lobed wave. Those of you who have taken chemistry have noticed this one it's called a p orbital. In this case, it's up and down only. There are two other p orbitals that are possible that are horizontal, but in this case, it has a red lobe that might be a crest and a green lobe that's a trough. And then it waves through the colors again, too, as time goes on. As I'm saying this, I'm not feeling very satisfied with having conveyed to you the idea that these are really our standing waves around the nucleus. Any questions that would prompt me to clarify it better? Yeah, Daniel? Okay, so the question is in modern theory that you can't pinpoint an electron, you rather find it in this dispersed arrangement. If you take hydrogen, just let it sit there, one hydrogen atom, which normally hydrogen comes as pairs, but you break it apart, you set a hydrogen there and let it sit and let it sit, wait, you'll discover it, and don't look at it very carefully, because there's this issue of when you look at it, you bother it. It will be in this state. That is, its electron will be in this orbital, pure and simple. It will be cycling along in time through, in my drawing, through the colors. In the real world, it's got this evolution of a wave phase. Just like a water wave going by you has a phase from crest to trough to crest to trough. It's doing that, but here the phase is cycling in this sort of immaterial, abstract space. If you go looking for the electron, though, so while it's left alone, it has the electron is dispersed around it. It is present all around the nucleus. It's not at any one place at one time. If you go looking for it with a proper microscope, and this is already a challenge, the proper microscope to see this involves sending things at it. And to see great detail in an atom, you have to send very energetic things at it because you can't resolve. Remember, waves can't see structure that's much below their wavelength. We saw that in the context of the microwave oven. The microwaves in a microwave oven cannot resolve or detect the holes in that front window because the holes are too small. The wavelength of the wave is about like this. The holes are like that. It can't sense them. So similarly, if you want to send a wave at this hydrogen atom and see its structure, that wave has to have a wavelength that's considerably smaller than the size of an atom. It's possible, such things exist. X-rays, gamma rays do have that kind of energy. But they're very energetic things, as we'll see, and they have a big effect on what they see. So if you go looking for where the electron is, you can locate it. The looking for it, you might think that secretly, I've told you it's in that ball all around the nucleus, but secretly, oh, it's really located somewhere, right? No, it actually isn't. It's truly everywhere. When you go looking for it, you either see it or you don't see it. And it's a statistical thing. It is a rolling dice that the universe pulls on us. We cannot predict where you will find it. But if you go look for it and you do find it right here, the act of finding it there, and also the act of not finding it there, changes the future for that electron. If you found it right here in a tiny spot, you discovered it's within this tiny little volume, much smaller than an atom. In the next moments of time, you will have imparted a huge amount of energy into that electron in the act of finding it. And it will suddenly no longer be bound to that atom very well. In all likelihood, it will fly all over the place because you localized it tremendously in space. You pinned it down. And once you pinned it down, it's a new wave. It's a wave. Imagine that you had a wave on the ocean that was all nice, smooth, undulating thing. And you went looking for the wave. And suddenly, you have localized the wave to a spike. So all the water is now flat around there because you know it's not there. It's now a spike because you've pinned the wave down into the spike. And it's very tall. And the next moments of time, it's not going to be that smooth, undulating wave it was before. Now suddenly, it flies out in all directions. The same thing happens to the electron. The act of localizing it changes the wave so that it's one that's full of all kinds of things heading off very fast in all kinds of directions. Is that okay? All right. Having told you about this story, so for electrons, just in general, I'm running late in time here, and I want to say something. So before the quantum era, which is the early 1900s, people thought the world divided into things that were wave-like and things that were particle-like. Billiard balls, particle. They thought also electrons, protons, as far as everybody can tell at that point, atoms, they're purely particle object things. What were wave-like then? Well, sound, light was thought to be wave-like, was known to be wave-like. That does it best. It turned out, though, as people started looking more deeply into both the things they thought that were particle-like, like electrons and protons and billiard balls, they discovered, oh, they've got a wave-like character after all. An example of this is what's known as the Davison-Germer experiment, where people discovered that electrons sent through a crystal underwent interference effects. Interference effects like the soap film, that's a wave phenomena. And here it was, electrons were exhibiting a famous wave phenomena. So evidently, the things that were thought to be particle-like aren't as particle-like as all that. And how about wave-like things? People discovered that light has a particulate character to it too. And this comes about, the classic example of this is what's known as the photoelectric effect, which the explanation for which is what Einstein got his Nobel Prize for. Amazing. The Davison-Germer experiment was a Nobel Prize experiment showing that electrons have a wave character. The photoelectric effect was a Nobel Prize experiment showing that light has a particulate character, and Einstein, he never got a Nobel Prize for relativity. He got it for this effect. The effect is this, that if you shine light at a surface, the light can cause charged particles to come out of the surface, like electrons. And the classic expectation was as you turn the intensity of the light up, so you got stronger and stronger electromagnetic waves, more electric fields, ooh, you'll get more and more energetic electrons coming out. And that's not true. What mattered wasn't the intensity of the waves, it was the frequency of the waves, or equivalently their wavelength. The shorter the wavelength and higher the frequency, the more energetic electrons came out. Evidently, the light was being absorbed in a particulate manner, all or nothing, and what mattered was the frequency. The higher the frequency, the more energy was being absorbed in one of those particulate pieces, what are called photons. So the blue lights, the ultraviolet lights, the X-rays, the gamma rays carry more energy in their particle character. This ultimately is why ultraviolet light and X-rays are potentially damaging to us. Their particulate character involves lots of energy on a molecular scale, and they can do damage to molecules. They can rip them apart. They're called ionizing radiation, and they can cause skin cancer and stuff. So, having run us out of time, we'll come back to this gook on Monday.